Okay. So, our ultimate goal here today is to be able to count atoms by weighing them. So we'll start off with a weight and end up with a number of atoms. Okay? We haven't done that before. We went from moles and atoms, but we haven't done weights to atoms. Okay. So, go to the grocery store. They price things in the grocery store in 3 different ways. When you go to the butcher shop in the back, they sell you stuff by how heavy it is, right? So we can measure mass. Then you stop by the soda aisle or the dairy section, and they sell it to you by how many gallons it is, or how many liters, what volume you have. And we're glad they don't price potato chips that way, because those bags are always huge, but they're usually mostly empty. How do they get away with that? No, really, how do they get away with it? The answer is, because if you read very carefully on the package, it will say, this is sold by weight, not by volume. Some settling may have occurred during shipping. Yeah, some settling, it's only got 1/4 chips and 3/4 air. But they told you, we're not selling you by how bad. We can fill it all up with air. We're only selling you the chips in the bottom. And we're going to sell it by weight, not by volume. Okay. But there's a third way you buy things in the grocery store. And that's the way you buy eggs. You buy dozens of eggs, right? It's how you buy donuts. They don't weigh the donuts they sell you, right? They count them. And usually it's dozens, or baker's dozen, which is 13. But okay. So we need some units for these. In the metric system, we've talked about some of them. Okay? We buy steaks by the pound. What are they going to use in Europe? In place of pounds, they use kilograms and grams in place of pounds and ounces in Europe. Okay. Actually, volume is the one place where we went half metric, because we buy our sodas in the metric unit, liters. And we need a metric unit that means a number of pieces, like dozen. We need one that's a little bit bigger than a dozen. And there are lots of words that mean numbers. Dozen means 12. A gross is a dozen, so it's 144. A score. Abraham Lincoln given the Gettysburg Address said 407 years ago. A score was 20. By paper by the ream. A ream is 500 sheets. Okay? So there's lots of words that mean numbers. The word that means numbers in chemistry, the word means the number in chemistry class is mole. That's the word that means the number. Mole just means the number. Somebody says dozen, you think 12. Someone says mole, you think of this number. It's a big number. Okay? It's bigger than 12. So, they had to pick a number. And this is the number they picked. They picked the number of carbon atoms in exactly 12 grams of carbon-12. Now, at first glance, you look at that, you say, well, that's pretty random. But actually, it's the exact opposite of random. Random means you pick anything. No, they picked something very, very specific tied to stuff we've learned before. It's not random that they picked carbon-12. Because you should have written about carbon-12 today in your bell work. Right? You should have written about carbon-12 in your bell work today. So, how many atoms do you think that is? So 12 grams of carbon-12 is a block about carbon about this big. like a centimeter on a side. And it's going to be a big number because atoms are small. So, if I was going to write out that number, would that be enough zeros at the end? No, it would only be thousands, right? How about that? Would that be big enough? No, it's only millions. How about millions of millions? Is that enough zeros? It's pretty big, though, isn't it? Atoms are tiny. There's going to be big, and millions of millions, trillions, that's a lot. But no, we need some more zeros. Well, no, actually, even that's not enough zeros. And finally, we're out of zeros. In a piece of carbon this big, there are that many atoms. Try to say that number out loud.
656 billion.
No, septillion. It's the seventh. Sex is only 6. This is septillion. Okay? Huge. By the way, septillion is not official. It makes sense that it would be that, but it's not really official. Okay? So, but that's a big number. Okay? 6.022. We usually only do it at 6.02. It's okay if you drop that second 2. They actually know it to 10 digits. So we're rounding off anyway. So I think your textbook cuts it off at 6.02. They just round it off someplace different. It's the same number, just rounded off. Okay. Okay. But it's like a dozen. It's just a number. If I have a dozen eggs, I have 12 eggs. If I have a mole of eggs, I have 6.02 times 10 to the 23rd eggs. Which would be kind of big. Okay? That number is actually called Avogadro's number. So I thought about, hey, I'm going to get you, I'm going to show you a mole. So I was going to go buy some BBs. I was going to buy a mole of BBs, because BBs are kind of tiny, right? But I ran into a problem in that my box was a little bit too big. If I wanted to buy a mole of BBs, the box was a little big. Try to picture how big a box that would hold a mole of BBs. Hold that many BBs. The size of this room, that's pretty big, isn't it? So actually, let's do the math. Okay. Now, this is a cube, right? Okay, and it's got 10 along each side. So it's 10 times 10 times 10, 1,000 cubic centimeters, right? So if I take the number along the side and multiply it by each other, right? If I take the number along the side and multiply those 3 times, that will tell me how many pieces there are. But if I had this many BBs, I can do the opposite of that and take the cube root to figure out how many BBs would be along each side of my box. Because 10 times 10 times 10 gets me 1,000. A cube root of 1,000 is how long each side of the cube is. Well, if you take the cube root of that number, you get 84 million. And let's just say a BB is about a millimeter across. Is that fair? So my box would have to be 84 million millimeters. Which would be 84,000 meters, which would be 84 kilometers, which is 52 miles. So if I wanted to buy a box of BBs, I would need a box from here to LA long, from here to LA wide, and from here to LA tall. There's a reason I did not bring in a box that was full of a mold of BBs. Okay. The word they use to describe Avogadro's number is unimaginably big. You couldn't imagine that it was a box 50 miles on a side. Okay? Because BBs are tiny. Okay? Now let's take the other side of that. Okay, that's one BB in the corner of that box, right? A box 50 miles long, takes the place of an atom in a box of carbon this big. Atoms are that small that if you took that 50-mile box and squeezed it into a box this big, in the corner you would have one atom if you took the BB and squeezed it just as much. So atoms are unimaginably small. You can't picture anything that small. Your brain doesn't go that far. It's a limitation of your brain. It's not you, it's everybody's brain. You can't think in numbers that big or that small. But we can do the math and say it works. And they've checked, it works. Okay. So it's called Avogadro's number, after a scientist. He didn't find the number, but he was the one who said it's the number of pieces that's important. Okay. So I can write that like this. Hey, I've seen things that look like this before, where I had something equal to something. Once I can write that, what can I make? Conversion factors. It's why we learned it, folks. We learned it. And we did it with moles before. Now we're just learning what that mole really is. Okay? It's a really, really big number. So all we have to do is go through those same questions. What do you want to get rid of? Where's it got to go? What can you change it into? Right? We've done those problems over and over again. This is why we did them, so we can answer questions like this. How many atoms are there in 4.56 moles of carbon? And I say, I hate doing math, Mr. Green. Would you rather count? Because if you wanted to count to that number, if you had started at the beginning of the universe and counted one every second since the beginning of the universe 14 billion years ago, you'd be less than 1/10 of 1% through that number. There have not been a mole of seconds in the history of the universe. It's a big number. I said unimaginably big. There's 1/10 of 1% of that number is about how many seconds there have been in the universe. Okay, so I got 4.56 moles of carbon. What unit do I want to get rid of? Moles of carbon. Where's it got to go? On the bottom. What can I turn moles of carbon into? Atoms of carbon, because we just said that 1 mole is always Avogadro's number, 6.02 times 10 to the 23rd atoms of carbon. Doesn't matter what kind of atom it is, it's that many pieces. I mean, when you buy donuts, it doesn't matter whether they're glazed or filled, they're still donuts. Okay. So it's 4.56 times 6.02 EE23. And I get 2.75 times 10 to the 24th. And the only unit I have left is atoms, carbon. So if I ask you how many atoms are in that many moles during the test, you have two options. You can use math, or you can start counting. If you start counting, you're unlikely to finish the quiz. Okay? So no matter how bad you think the math is, it's better than counting. Are we in agreement? Okay. Well, if it works one way, if I give you moles, you can figure out atoms, then it's got to work the other way. That if I give you atoms, you can figure out moles. So 5.87 times 10 to the 22nd atoms of iron. And all I want to do is talk about those atoms of iron in a different unit. So I just want to convert it. So what unit do I want to get rid of? Atoms of iron. Where's it got to go? The bottom. What can I turn atoms into? Moles. So 1 mole is Avogadro's number of atoms. So the number next to moles is 1. Number next to atoms is 6.02 times 10 to the 23rd. So 5.87 EE 22nd divided by 6.02 EE 23 equals 0.0975 or something, yeah. 0.097, 0.0975, and those are moles of Fe. Extra super hard? Find two things that are equal, make conversion factors. Now, on the last test, you made conversion factors with moles already. But it wasn't to atoms, it was to grams, right? So, because that's the issue. How the heck am I going to get that number? Am I going to be able to count to get that number? No, I can't count. They must have gotten that number some other way besides counting. Everybody agree they had to get it some other way? Because we haven't been around long enough to get it to count that high. So what can we measure that will tell us moles? Well, hopefully on your bell work, this is what you wrote the AMU was. 1/12 the mass of a carbon-12 atom. So 1 AMU equals 1/12 carbon-12. Or another way of saying this is 12 AMUs equals 1 atom carbon-12. Well, because if 1 AMU is 1/12 of what carbon-12 weighs, then carbon-12 weighs 12 AMUs. Does that make sense? Okay, now, did you notice that carbon-12 showed up on today's definition of moles? Okay, that was not an accident. They did that on purpose. Because the mole is the number of atoms in 12 grams of carbon-12. So 12 grams of carbon-12 is 1 mole of carbon-12. This is why they did it. This is why they defined them both on carbon-12. Because if they're talking about atoms, 12 AMUs is 1 atom. But if I'm talking about grams, 12 grams is 1 mole. So we said the average atom weighed whatever was at the decimal number on the periodic table in grams, right? So if I look up sodium and it says 22.99, that means the average atom weighs 22.99 AMUs. But we also said it was 22.99 grams for 1 mole. The decimal number on the periodic table is the average atom in if it's in AMUs, it's what the average atom weighs. If it's in grams, it's how much 1 mole weighs. The same number means two things based on what unit you put after it. That's why they picked it, so they wouldn't have to write two periodic tables, one for it in AMUs and one for it in grams. They knew it was going to be an issue. So they defined them both on carbon 12 so that you could talk about it in terms of atoms individually or in groups of atoms, moles. That's why they made them both based on carbon 12. So when you're doing the atomic mass practice, you looked up this number, right? On the last test, when I gave you so many grams and asked how many moles, you looked up this number. It's the same number, right? You looked up the same number and used it for two different purposes. And it works because they designed it that way, so it would work for two different purposes. It wasn't an accident. Okay? So that is called the atomic mass. So when I look up beryllium and it says 9.01, 9.001 AMUs is one atom, the average atom. 9.01 grams is 1 mole, a whole bunch of atoms. So I'm going to go to the periodic table and I'm going to look up some numbers. First of all, I look up carbon, and carbon is 12.01 grams, is 1 mole of carbon. Okay? And 1.01 grams is 1 mole of hydrogen. All I'm doing is looking up numbers on the periodic table. And 1 mole of iron is 55.85 grams. So this right here. Okay? So that means that if I have 12.01 grams of carbon, 1.01 grams of hydrogen, or 55.85 grams of iron, I have exactly the same number of atoms. It's just that the carbon atoms are heavier than the hydrogen atoms. If I had 1 million skateboards and 1 million cars, I'd have the same number of pieces, but one of them would be heavier than the other. Okay? Because these are all 1 mole, they're all Avogadro's number of pieces. Whoa. I already wrote it that way, but that works because they're all 1 mole. So I can write down that 12.01 grams of carbon is 1 mole of carbon. I look up carbon on the periodic table, it's 12.01, that many grams is 1 mole of carbon. Hey, I got two things that are equal to each other. What can we make out of these? The same thing we did with this last time. This was on the last test. We went between grams and moles. Okay, but what we probably didn't recognize, that one side is about how heavy, the other side is about how many. so we can count things by weighing them. Because if I give you a weight, you'll be able to get rid of the grams and change it into moles. I'll start off with how heavy it is. I'll end up with how many I have. And then if I want to be specific, I can take those moles and change them into atoms. How many atoms there are. And that's actually the only new math, because we did the other stuff on the last test. So let's do a few examples and we get to start on the practice. So how much would 2.34 moles of carbon weigh? So, what unit do you want to get rid of? Write down what they gave you, 2.34 moles of carbon. What unit do you want to get rid of? Moles of carbon. Where does it have to go? Bottom. What can I turn moles of carbon into? They want weight. Do I know about moles and grams? Yeah, I do. Because I've got a periodic table, I can say 1 mole weighs 12.01 grams because it's carbon. If it's not carbon, that's not 12.01. And if you push those buttons on your calculator, you get 28.1, I think. This is what we did on the last test, right? And we did it backwards. No, so this is just a reminder of the old, how the problems were before. So let's talk about what the new ones look like. How many atoms in 1 gram of lithium? Back in a second. So I start off with 1.00 gram of lithium. Okay. I can go from grams of lithium to moles of lithium. We just did that a second ago, right, with carbon. So it works with lithium too, it's just a different number. So the 1 is next to moles, and the number next to lithium is 6.94 off the periodic table. But now I don't have the unit, so I want to get rid of moles of lithium, so it's got to go on the bottom. And what I want to change it into is atoms of lithium. And now I don't have to look up the numbers because they're always the same. 1 mole is 6.02 times 10 to the 23rd pieces. Just like dozen, it's always the same. Mole is always the same, just a much bigger number. So 1 divided by 6.94 times 6.02 EE 23 equals 8.67 times 10 to the 22nd atoms of lithium. And no matter how much you hate conversion factors, it would be better to do the math than to try to count. I started off with how heavy it was. I ended up with how many I had. You can weigh things to count them. Well, if I can weigh things to count them, if I counted them, I can tell you how much they weigh. right? So how much would 3.45 times 10 to the 22nd atoms of uranium weigh? Hey, what do I want to get rid of? Well, atoms of uranium. Atoms of uranium, I want weight, but I can't turn atoms into grams. But I can turn atoms into moles. Because 1 mole is always the same number of pieces. And then I can take the moles, get rid of those, and turn those into grams, because I have a periodic table. My periodic table next to uranium, it says 238.03, and that's the grams. So 3.45 EE22 divided by 6.02 EE23 times 238.03 equals 13.6 grams of uranium. So I start off with how many? I could figure out how heavy, counting things by weighing them. Usually, and I'm sure I said this last chapter, people ask, do I have to keep writing uranium? And the answer is yes, because eventually we're going to do conversion factors that change that uranium into a different chemical and leave the other start the same. Mr. Green? Yes? Will do. You're welcome. Bye. Okay, so really complicated? So the key is, if they don't give you moles, you got to get to moles so you can turn it into what they asked for. Just like if you had a prefix, you had to get rid of it so you can turn the base unit into something else. With whatever they give you, you got to turn it into moles so you can turn it into what they asked you for. Make sense? Okay, so mole practice number 2. There's not hundreds of them. Okay, there are a few on the back. Don't forget to do the back side.